In this question, what we've got is a situation where we've effectively been presented a hydrocarbon. It's been burned, and we've been asked to determine the empirical formula of that hydrocarbon. The context we've been given is that the hydrocarbon was burned in excess oxygen, and we've been told the mass of carbon dioxide produced and the mass of water produced. Now, based on the fact that in the question we've been advised that the hydrocarbon was burned in excess oxygen, there's something quite important we can infer from this, which is the fact that this was effectively a complete combustion, right? So effectively, what that means is simply that this combustion took place under conditions where the amount of oxygen available was not a constraint, in the sense that there was not a lack of oxygen. And the implications for that, as far as the reaction goes, is that because there was not a lack of oxygen, all of the products from the combustion are the carbon dioxide, primarily carbon dioxide and the water. But beyond that, the specific relevance to this question would be the fact that in terms of the carbon that was present in the hydrocarbon, all of that carbon would have translated into carbon dioxide and not other products, such as for example, in an incomplete combustion, one of the products we might expect would be carbon monoxide, right? So CO, carbon monoxide. But we've been advised here it's excess oxygen, so we can assume in this particular instance, okay, well, what the question is saying is that the carbon that was in the hydrocarbon has been converted into the carbon in the carbon dioxide, effectively saying that there's a one-to-one ratio in terms of that the moles of that particular carbon. Now, in order to progress in this particular question, to kind of solve what we've been asked to solve, one of the things I'm going to try and do now is work out what the molar masses are, because we want to convert these into moles so that we can really compare the actual number of atoms. So what we're going to do, we need to work out the molar mass, right? And from that we can work out the moles. And that follows from the equation of moles, which I'm going to put as N. So moles is equal to the mass, and in this case I just write the mass in grams, divided by the molar mass, right? So MR, and that would be, in this case, in grams per mole, right? Now, for the molar mass of carbon dioxide, if we refer back again to the elements we've got here, you may actually know what that is already, but I'm just going through this process just for clarity. So for the moles of carbon dioxide, that would be 12, right? So we're taking the relative atomic mass of carbon, multiplying it by the occurrence of carbon in the formula. So it only occurs once, so that's times 1, plus the occurrence of the next element, so that's oxygen, which is the relative atomic mass is 16. It occurs twice, so that's going to be times 2. And if you do that, you should get 44, right? Now, if we do the same thing, but for H₂O, right, for water, what are we going to get? So we're going to get H2, right? So that's going to be the 1, which is relative atomic mass of hydrogen multiplied by 2, multiplied by the relative atomic mass of oxygen, which occurs once, right? So that's going to be 16, and it occurs once, right? So that's going to give us 18, right? So here we've got that the MR of CO₂ is 44, and the MR of H₂O is 18. Okay. Now, taking those two molar masses, we now need to go and use those molar masses to work out the moles of each, right? So we're working out what the moles of, so that's the N, right? So the moles of carbon dioxide is going to be, as we've shown here, that it's going to be 195.712 and that is going to be divided by 44, right? And in the case of the moles of H₂O now, that is going to be 70.056 divided by 18, right? And I would invite you at this stage to work out both of those on your calculator and see what you get. Okay, so if you had to go at working that out, what you should get for this one, 195.712, etc., etc., is 4.448, and in the case of H₂O, for this one, what you should get is 3.892, right? Now, one of the other things we do need to pay attention to is, at this stage, is what does this actually mean in the context of what we're really looking at, which is the ratio between carbon and hydrogen, right? Not the ratio between CO₂ and H₂O, but the ratio of carbon and hydrogen, right? So what we really want to look at is the ratio of carbon and hydrogen, the moles of these. Now, what we can quite clearly see is that with carbon and its ratio, so for every mole of CO₂, how many moles of carbon do we have, right? So for every mole of CO₂, we have 1 mole of carbon because it's C and it's only 1, right? So we can, from that, deduce that the moles of carbon here is actually 4.448, right? Now, in the case of hydrogen, it's not quite so straightforward. It's not a 1-to-1 ratio. For every mole of H₂O, we do not have 1 mole of hydrogen, right? Because as you can see, this is H₂O. So therefore, because of that too, we can deduce that for every mole of H₂O, we've got 2 moles of hydrogen, right? So for us to then figure out, okay, well, what's the comparison? The moles of carbon, the moles of hydrogen, actually we need to multiply this by 2, right? So we need to do 3.892 multiplied by 2. Okay, so at this stage I would invite you to have a go and work out what that is going to be. Okay, so if you did have a go of working out what that is, what you should have gotten is 7.784, right? 7.784, and that is our moles of hydrogen. So that's like 3.892 times 2, right, is 7.784. Now, in terms of empirical formula, we know that in order to achieve the empirical formula, what we need to ideally try and get is a whole number ratio, the smallest whole number ratio, so should I say the simplest whole number ratio that we can. Okay, so how are we gonna try and approach getting that? In this case, at this stage, what I'm going to do is divide both sides of the equation by the smallest number, right? And the smallest number which we currently have is the 4.448, right? So I'm going to divide 4.448 by itself, and I'm going to divide 7.784 by 4.448, right? Now, obviously, because this is being divided by itself, this is going to give us 1. But I would invite you to have a go and figure out, well, okay, when we divide 7.784 by 4.448, what are we actually going to get? Okay, hopefully you've had an opportunity to have a go at what that is. If you did that, what you should have got is 1.75, okay? 1.75. So I'm just going to write this out again just because this is maybe a bit too close to, but here we've got that now the ratio of the moles of carbon compared to the moles of hydrogen is 1 to 1.75. And as we mentioned before, we're looking for the smallest whole number ratio. Clearly what we have is a ratio, but it's not the smallest whole number ratio because this is not a whole number. So what we need to do at this stage is what I would describe as scaling up effectively. And what scaling up effectively consists of is you're multiplying both sides by a number such that the two values get as close as possible to being a whole number ratio, right? And this is, of course, at this stage, the focus is on getting the hydrogen to being a whole number. So if we take 0.75, you can do this on your calculator. You can play around with a few integer values. Start at 1. Well, I mean, if you start at 1, it's not going to help you, but you can start at 2 and go from there. So multiply it by 2, see what you get. Multiply it by 3, see what you get. Multiply it by 4, see what you get. Multiply it by 5. If you actually have a go at this, you will find you don't need to get up to 5, but but anyway, it's that kind of systematic process and seeing how close you can get to a whole number ratio. So if we were to multiply this by 2, what do we get, right? So if we do that, we should get effectively 1.5, right? Yeah. And if you've had a go, you may have already come up with what the number would be that would get it to a whole number. But just for the sake of, I don't know, thoroughness or completeness, let's go ahead and multiply by, so this is times 2, multiply by 3 as well, so times 3. So I invite you to have a go at, okay, well, if you multiply by 3, what do we get, right? So if we do that, we're going to get 2.25, right? And then have a go at multiplying it by 4, right? So if you do multiply it by 4, you should find that you do get a whole number, right? And that is going to be 3. Yeah. Now, just to clarify, this exercise I just did on the side is not the actual number that we're working with. I just chose to isolate the part of it which is not a whole number to show you how we eventually get that part of it that's not a whole number to a whole number. So realistically, what we're actually working with here is 1.75, right? So I'm not going to adjust all of these because these relate to the 0.75. But if we take 1.75 and we integrate that into what we're meant to get here, what we need to do is take the 1 and multiply it by 4. So 1 times 4, obviously that's 4. So this, we just add that side to what that was. So that's the 4, add it with the 3, and we get 7, right? Therefore, this is a whole number that we get, 7. So what we can do here, if you multiply both sides by 4, alright, so I'm going to just put in brackets that we've multiplied both sides by 4. What we're going to get at the end is 4 and 7. Okay, so are these our simplest whole number ratios? Well, yes. Okay, because if we divided it by 2, we're not going to have a whole number on this side. If we divide it by 3, again, we're not going to have a whole number, etc., etc. Right? Therefore, our empirical formula, remember, this is the ratio between carbon and hydrogen. So empirical formula is therefore C4, and our ratio is obviously, as you saw, is 4 H₄O, right? And if we put this in like an, well, no, not did I just write 4? I did not mean to write 4. Yeah, that was my bad. That was meant to be a 7. So C4H7, right? So, but we as I said, we need to. I was basically thinking ahead. So C4H7, right? So this would be in an acceptable format. This would be our empirical formula, right? Okay.